Okay. I would like to start by thanking the conference organizers for what's turning out to be a very exciting conference. I'm already learning a lot. And the two speakers before me in my panel, I think, did a fantastic job of starting to tell you the direct and indirect ways in which science impacts society. And I was asked to talk about how astrophysics impacts society. And I would like to take a three-pronged approach to that because there are actually really many different ways in which one can talk about this. So I would like to do a little bit of each. One of them is saying that astronomy has, in fact, shaped society for a very long time. And I don't just mean using astronomy and stars for navigation in the old times, but really the beginnings of modern science date back to astronomy. So it has been a long time in the making that astronomy has its impact on scientific thought. A second direction that one can take is astronomy as a spearhead for technology. All of the unintended consequences of developing tools for astronomy that ends up impacting society and technology in a very, very real way. And maybe above and beyond all of that, what we can say about astronomy is that it's the ultimate expression of human curiosity and human exploration. Just like we discovered different parts of our own world, astronomy is now allowing us to, and astrophysics is allowing us to discover what lies beyond our world and satisfy that curiosity. So I would like to do a little bit of each of these three approaches to astrophysics and society. Oops. Okay, so on the first point, how has astronomy influenced society? Well, as I said, astronomy was one of the first quantitative sciences, so it allowed us to transfer from merely observing nature to a mathematical description of nature. I'm going to give you an example of this. From mathematical description to the ability to make predictions, which is the cornerstone of modern science. And it formed therefore it formed the basis of modern scientific thought. So I will show you a very strange phenomenon in the sky. I'm sure a lot of you are familiar with this, but maybe you haven't thought about it recently. When you do astronomical observations of the planet Mars from Earth, which ancient astronomers and Middle Age astronomers have done, it looks like something like this, night after night. So the days are running here. At some point in its orbit, Mars appears to go backwards. And this confused ancient astronomers and scientists by quite a lot. So why does Mars do that? Why does it go back in its orbit? Of course, now we know the answer. It's very, very simple. Mars has an orbit that's a little bit farther away from the sun, so its speed around the sun is a little bit slower. So just like a slower car next to you, even though it's going forward, looks to you like it's going backwards, there is a part of its orbit in which Mars appears to us as if it's going backward. Now, even though this is extremely simple, of course, it doesn't fit in a worldview where the Earth is the center of the universe or center of what we now know to be our solar system. So this is the first indication of the heliocentric model taking roots. And the Copernican revolution, what we call the basis of modern scientific thought, started with placing the sun at the center of the solar system. You might say it's very simple, but it solved a lot of problems, and it really revolutionized the way in which we started thinking about observations, about data, and about making sense out of what we're seeing around us from our observations. Now, Copernicus is not the end point of this. It's in fact the starting point, followed by Kepler and his famous laws of planetary dynamics. Why is Kepler important? Because he then took these observations and he took this heliocentric model and developed it into empirical laws, which were then predictive. So the first mathematical representations of the phenomena, the scientific phenomena that we see, started with Kepler. So that's why we give Kepler a very, very important place in history, and we credit him with a lot of things. In fact, a recent NASA satellite that is dedicated to finding planets was named after Kepler. So I don't necessarily like putting up pictures of old dead men, especially in an audience like this where there are lots of budding young scientists and a lot more women represented here than back in back in the 1500s and 1600s. But just for the completeness of my story about how astronomy has been the first quantitative science, obviously Kepler was followed by Isaac Newton's laws of gravity, where he then took some empirical laws and made scientific forces out of them. So the law of gravity that Newton formulated following Kepler then formed the cornerstone of what was to come. Of course, Newton's theory was then superseded by Einstein's much later in 1915, but nevertheless, this just shows you the development of how we think about gravity and how we started thinking about the universe. So along these lines, what I mentioned is that we went from just describing nature to mathematically describing nature to being able to make predictions. And one of the first examples of that that I know of is that the existence of Neptune, the 8th planet in our solar system, was actually predicted before it was discovered. So Monsieur Le Verrier noticed that the way the planets moved around must be due to the existence of another planetary body in our solar system before it was detected. And he called his colleagues in the Berlin Observatory, and sure enough, they turned the telescope to exactly where he predicted. And there you go. Neptune was discovered, and this is the Bureau of Longitudes of Paris announcing the discovery of Neptune. So we now start becoming a predictive science. And just as an aside, this is today how we still find planets around other stars. We apply Kepler's laws, and we look for small dithering in the star itself, and we find many planets this way. So let me go on to my second way of approaching astrophysics and society, which is astrophysics as a technology driver. There are literally tens of examples that I can give you. I'm just going to do a few. And I know that solid state also has many that it can boast about, but astronomy maybe predates it by a little bit, let's say. Okay, so maybe many of you know this, maybe you're not aware that we are now so dependent on GPS, right? We can't read maps anymore. We have to put in some coordinates on our phone or on our GPS in our car in order to get somewhere. Did you know that GPS would not have worked if it weren't for Einstein's laws of gravity? So if we just applied the Newtonian law of gravity and did not do the time corrections to the satellites that are due to these geometric bending of space and time, GPS satellites would not work. So we rely on a network of 24 GPS satellites around the world, but as this little diagram shows, clocks tick faster where the space-time is warped less, so far above the Earth, and they tick slower where the warp of space-time is more, which is closer to the surface of the Earth. And since we rely on very precise timing from these 24 different satellites around the world in order to find an exact position, a useful position, we actually have to do this correction on our global positioning systems. So when Einstein wrote down his theory of general relativity, obviously nobody could foresee that global positioning system one day would rely on this, or that we would all be lost without it. Another example, again, originating from astronomy that I like very much is the charge-coupled devices, CCDs. They were devised for astronomical use in order to capture images, in order to be able to expose the telescopes and collect light to faint astronomical images and record this for a very long time. So we went from photographic plates to CCDs, first used in astronomy in 1976. And I don't need to tell you in how many areas of life we use CCDs right now. Very quickly, it became a part of our cameras. Obviously, our new telescopes all rely on CCDs. This is an example from the Hubble Space Telescope. And in the medical field, endoscopy is nothing but a CCD camera that is on a flexible wire. So the endoscopy technology itself owes its existence to CCDs. Let me give you one more example, especially one that I'm going to come back to in a little bit, which is something called aperture synthesis. And that's a fancy word for being able to combine signals from different telescopes in order to be able to get a resolution that you would not be able to get from a single telescope. It was developed by Martin Ryle, the radio astronomer in the UK, and a Nobel laureate in 1974 for this discovery, as well as his other contributions to radio astronomy. And he basically devised a way in which wave fronts from different sensors could be combined in order to, and correlated in order to get the resolving power of two telescopes, or a bigger telescope, when what you really had was two smaller telescopes. Now, it might sound very, very far removed from medical imaging, but this is the mathematical basis and the scientific basis for how CAT scanners today work, how MRI works, how PET scans work. So for those of you in the medical field, and I know there are a lot of you here who work on imaging, you're welcome. So I could go on and on. I could give you examples of how the space program gave you non-stick pans. I could tell you how astronomy developed the wireless local area networks that we are, again, very, very dependent on today. But I kind of don't want to do that, because that's really not why we do science. So let me take my third avenue down to astronomy and society, which is what I would like to call astrophysics just because. Just because we are curious as humankind, just because we have an explorer spirit, just because we want to know where we came from, who we are, and where we're going. Are we alone in the universe? Do we have is there only one universe? Are we unique? How big is the universe? These are all questions that I think make a lot of us maybe not stay up at night as much as it makes me stay up at night, but at least it's deep, rooted deep down in our beings, that we want to know a lot more about our place in the universe and whether we are alone and what the fundamental laws governing the universe are. So I think maybe, even though it doesn't look like it has a direct impact on society, just because we are curious humans and we love exploring, I think this is maybe the biggest impact that it has. So a few examples. One of them is the cosmic microwave background that showed definitively that the universe has a beginning, that there is a Big Bang that happened 13.7 billion years ago. And very nicely, very kindly to us, it actually left a relic radiation in the sky, everywhere in the sky, that is uniform to 1 part in 10 to the 5, so almost like 10 parts in a million, except that we have been able to develop satellites that can measure that 1 part in 10 to the 5 differences in the temperature in this relic radiation in the cosmic microwave background, and from that map out everything that we know about the fundamental parameters of the universe. Another example, we are all aware that we are not alone, at least in the sense of being the only solar system in the universe. In fact, the number of confirmed planets now exceeds 2,000. The number of planets that we suspect around other stars, so we have evidence for, but we just haven't been able to do the follow-up observations, are of the order of 6,000. And this is just one way of showing that wealth of discovery, that there are indeed planets like the Earth, planets like Saturn, planets like Jupiter, planets that are as close to the sun as we are, planets that are much farther away from their own star. So this is just one way of showing it in a diagrammatic form. So what is shown here is on the y-axis, this is the stellar flux in solar units, and on the x-axis, it's the distance from that planet from its, from that planetary system from our own sun, and the size corresponds to the Earth radii. So you will see that it goes from anything from as small as the radius of the Earth. There is actually an Earth twin that we've discovered, to as big as about 25 times the size of the Earth. And those are those bigger circles that you're going to see over here. So these are all the confirmed planets, and we have just begun exploring our solar neighborhood. And we have a long ways to go, and we're obviously looking into the question of not only are there planets, but are there habitable planets, meaning are there planets that are rocky and that are just the right distance from their own star in order to be able to support life, at least as we know it. It doesn't mean there's only one type of life in the universe, but obviously we're looking at we're looking first for things that we know how to identify. Now, in this last part of my talk, let me turn to something that is near and dear to my heart, or in other words, what makes me tick. And it's a good thing that it's black holes, because according to Ali's research, with a PhD in astrophysics, I'm a very ineligible bachelor. So I'm glad that I love black holes, and that's what my match is. So I apologize to my husband for that joke, but that's okay. So what I love working on these days is maybe the biggest, darkest secret in the universe, which is the black holes. And what is the appeal of that? Well, it is a prediction of general relativity. We have a lot of indirect evidence for the existence of black holes in the universe. From our own galaxy, black holes that are about 10 to 50 times the mass of our sun, to other galaxies where the black holes range from 1 million to 1 billion times the mass of our sun. And these are really enigmatic objects. This is one case where a physical theory predicts not only a singularity, what we call a singularity and infinity, but also shrouds that infinity in some kind of secrecy and says there is an event horizon, there is a part of the universe that is disconnected from outside observers where there can't be any information exchange. No light can come out, and everything that goes in loses its characteristics. So a black hole is maybe the simplest object in the universe. It's characterized by only 2 numbers, its mass and spin, and yet it really defies our understanding of all other physical theories where we think that we can turn time around and there is symmetry in time going backward and forward. And here, there isn't. So how do we explore black holes? As I said, maybe we're not satisfied with just the indirect evidence for black holes, where we can clearly see using Kepler's laws that there are billion solar masses in a dark, small area in the universe. So we actually use that very concept of aperture synthesis, or otherwise known as radio interferometry, to build a telescope as big as the size of the Earth. Why? Maybe because we're just audacious, because we can. And this will take us to realms of astrophysics that haven't been possible before. And in particular, what we want to do is look at the emission, the gas around black holes emit at a variety of wavelengths, all the way from radio wavelengths to sometimes even gamma rays. And there is a particular wavelength, which is a millimeter, in which the gas around the black hole allows us to see down to the event horizon. This the secret place that we're not really supposed to be able to see. And if we did, we should see a shadow, just like what I showed you in this picture. This bright crescent surrounds a dark shadow in the center. So what do? We connect telescopes literally across the Earth. There are 9 that are part of this project right now. It's called the Event Horizon Telescope Project. It's a very international project that University of Arizona plays a big role in. And what we see is a distant black hole, its signal arriving at multiple telescopes on Earth at slightly different times. They get recorded. And because of the particulars of these observations, a typical observation requires hundreds of terabytes of data recording. So it's quite astronomical scale, pun intended. And so that gives us the resolution to be able to see down to the shadow size, that shadow that I talked about, of our own Milky Way's black hole, which is called Sagittarius A star. So, as I said, we hook up lots of telescopes all the way from the South Pole to Arizona, to Hawaii, to ALMA, one of the telescopes that Arjan showed earlier, one of the big collection of radio receivers. Mexico is involved, European partners are involved, and we use these in a way that makes use of the rotation of the Earth so that different pairs of telescopes can look at the black hole at the center of our galaxy and receive signals from it simultaneously. And these huge amounts of recorded data are then combined. And just like you reconstruct what is there in a CAT scan, we reconstruct what is there from these different interferometric observations, what is at the heart of a black hole. So this is my colleague, Dan Maroney, at the University of Arizona. This is not the University of Arizona, of course. At this point, he's down at the South Pole Telescope, equipping it with the right type of receivers and masers that are necessary for this observation. And this is a great synergy, actually, between the University of Arizona and University of Chicago, because it's a PI telescope, the South Pole Telescope, run by John Kallstrom of the University of Chicago, and Dan Maroney is my colleague, professor, who's in charge of making it a part of this array that I talked about. Now, it's not enough to just hook up telescopes in order to get the signals. We actually have to do a lot of work in order to make sense out of this data. And that's what my group has been focusing on, a lot of theoretical work and a lot of computational work that makes sure that when we get these signals, that we can actually reconstruct it into the shadow of a black hole, and we can perform tests of general relativity that haven't been possible before. So what I want to show you here for fun, this is the hand of my postdoctoral associate, CK, and this is just a screen. It's a single GPU on his laptop, and what you will see here is a leap motion sensor. Right there. He's not actually going to type in commands, but he's going to treat it like almost like an Xbox or a Wii, and he's going to control the entire simulation in real time, including generating the images with his hands. So here we go. He's starting the simulation. This is time running forward. He's shot 1 million photons at this black hole on a computer, simulating everything that those photons do. He can zoom in and look at the ones that are trapped around the black hole. He can move around. Run it a little bit more forward. And because we are God in this context, we can also run time backwards. So what he's done is actually propagated the photons backwards in time, and now he's zooming out And what you will see is the shadow of the black hole imprinted on these ray of photons that have been shot at the black hole. There we go. So there you see it. This is what we can do on a single GPU. We've written algorithms that really tap into what CPUs cannot do, or it's not fast enough for us to generate simulations and really explore different characteristics of black holes. So we went to the NSF and we said, pretty please, can we have a bigger toy? And they gave us $2 million to build a GPU cluster at the University of Arizona. And at the time we did this 3 years ago, we were actually ranked number 7 in the Green 500 list, because it's not just how fast your computer is, but how energy efficient your computer is. And using the GPU technology allowed us to be very energy efficient. So needless to say, we play a lot with this toy, and we can generate lots and lots of different images. And there's just one last movie that I want to show you. This is about how I'm going to change the wavelength of light that we're looking at. So we're going to see the black hole first enshrouded in this gas. I don't think you can see it very clearly. Maybe we can turn off the light just for this movie. And what you're going to see is that there is this large cloud of gas swirling at the black hole. But when you get to the right wavelength, its heart, its event horizon is going to be revealed. Thank you. That's great. So as you can see, the frequency of light that we're looking at and the wavelength is changing. And all of that additional material is disappearing. By the time you get to a millimeter, you see that shadow and the crescent, the bright crescent right around it being revealed. And you can go to even higher frequencies, and that remains there. So this is what we're hoping to do. We're going to zoom into the heart of a black hole, and this project is ongoing. I'm actually going to go up on the mountain in Arizona in a few days for the first engineering data taking. Even though I'm a theorist and I'm not that useful, I like to be on the mountain. But the real data is going to come in early 2017 with the addition of ALMA and the South Pole Telescope and Hawaii. And we are actually going to be able to hopefully tell you in a year what we can learn. This is another fun thing that we play with. It's fun to be a student in my group. This is augmented reality with HoloLens. So not just producing these simulations, but also rendering 3D holograms of them so that more than one person can study it and connect different physical processes to what we're seeing. So I gave a talk at the American Astronomical Society just a couple months ago, and it attracted a lot of attention. The reason I'm showing that here is not to just give you a plug for the Event Horizon Telescope, but coming back to my point that I think deep down as a society, we just love to explore and we just love to know what's out there. And this was the coverage in the BBC. This was the coverage on NBC. And for the economists in the audience, maybe this is one that will impress you. It actually made it to The Economist. So let me just conclude by saying, paraphrasing a great scientist, when Robert Wilson, the first director of Fermilab and an architect of Fermilab, when the Congress asked him about the first collider that was being built in Fermilab, right here in Chicago, again, our home turf right now, when they asked him, how will the new accelerator affect the nation's security? And he said, it has nothing to do directly with defending our country except to help make it worth defending. So if I can paraphrase him, yes, there are a lot of unintended benefits of astronomy and astrophysics. Yes, there is technology transfer. But ultimately, in my view, I think it makes life worth living when we explore the universe. Thank you.